Microprofile for Artists, Deep Inspection of Rendering Sequence. In this advanced tutorial, we are going to investigate the most valuable rendering settings in details and tell which effects should an artist focus on for proper optimization of a Unigine world to achieve high and stable performance. We will go through the whole rendering sequence with the Microprofile tool, so make sure you have familiarized yourself with the Microprofile Basics video tutorial. Please note that rendering features will be considered using different projects to cover all of them here. The main purpose of optimization is to find a trade-off between performance and realistic look. The main procedures that performs rendering of a single frame is called rendering scene. It includes two main stages. Let's start with the first one, render shadows. The current world has a single world light source, so the only shadows rendered are the ones from this source. The four rendering shadow procedures below correspond to shadow cascades defined in the world light settings. Here they are. Use the Shadow Cascades helper to display them in the viewport. You can tweak the distance of the border of each cascade via the corresponding parameters. Reducing the number of cascades saves some time, so let's do it. Resolution of the shadow map significantly affects performance too, so let's reduce it also. Open the Settings window, as there are some global settings in the Render section that we need to consider. First, let's go to Visibility Distances and take a look at the shadow's visibility parameter. 500 meters is quite enough for observing shadows, so let's reduce the value. There are also shadow settings in the corresponding section. Further optimization may require decreasing quality of some features, such as soft shadows. You should also consider switching off effects unnecessary for your project. For example, linear interpolation for shadow cascades, or increased bitness of the shadow's depth buffer. Low quality of shadows can be compensated with screen space shadows. We will consider them later. You can also disable shadows at all and substitute them with baked voxel global illumination. Watch the global illumination tutorial for more details. Holes in alpha test surfaces can be ignored for better performance, but not in this case. You can see a significant performance gain we've got by just optimizing shadow settings. Now, the Render Shadow World block includes rendering of only two shadow cascades. Let's consider other types of dynamic light sources, omnidirectional and projected light. Rendering of shadows from an Omni requires 6 passes, so it may take too much time to draw real-time shadows for an Omni in all directions. We can adjust shadow map resolution. It's available for all lights. And we can also choose to render shadows only for certain sides of an Omni light source by using the shadow mask. The first 6 bits of it correspond to the left, right, front, back, top, and bottom directions, so we can enable a single pass if we don't need other ones. These simple optimizations give a noticeable speed up of shadows rendering. The second large procedure is the render screen. As a rule, it is the most time-consuming part of frame rendering. Let's go through all its contents. The Render Opacity G Buffer stage includes deferred pass for opaque and alpha test surfaces. The best practice on optimizing this stage are considered in the Content Optimization video tutorial. To find all alpha test surfaces in the world, enable the Alpha Test helper. As a quick solution, you can reduce distance scale. It affects all settings of distances in the world, so a large number of rendered polygons will be reduced at once. This is how rendering of G-buffer opacity can be optimized. The next stage is the Render Screen Space Bevel, which corresponds to the SS Bevel effect. You can find its settings in the corresponding section. Ultra quality does not differ much from low, but it is much more demanding in terms of performance. The next block represents rendering of decals. Recommendations on decal optimization are given in the corresponding video tutorial. Then goes the Screen Space Dirt effect, so let's open its settings. In most cases, there is also no need to use ultra quality in the highest resolution. Take a look at the effect at lower rendering settings. The Render Common Data procedure fills common buffers for the screen space features, SSRTGI, SSGI, SSR, and screen space shadows. So if we disable all of them, the Render Common Data will be skipped. Now we've come to the SSRTGI Screen Space Ray Traced Global Illumination effect, which might be very time-consuming. You can find its settings in the Global Illumination section. There are general settings and 3 subgroups for optional effects. The SSAO and SSGI effects will be rendered here if the ray tracing option is enabled for them. Otherwise, they will be rendered later separately. Optimization here may involve adjustment of the resolution, increased accuracy, fast tracing, and resolution depth parameters. The number of rays and number of steps parameters define ray tracing accuracy. Keep them as low as possible. We will consider settings of the sub-effects later at the corresponding stages. As you can see, these optimizations have significantly reduced computation time. The next Render Post-Material 2D stage is intended for rendering ambient lighting and reflections from the environment. It is not so heavy, but you can skip the stage by disabling the ambient and reflection parameters for each active environment preset if it is not necessary in your case. The next procedure includes rendering of deferred lights and the screen space shadows effect. We cannot actually decrease the time of deferred lights rendering unless we reduce the number of active dynamic lights, but we can turn screen space shadows off. The stage will be rendered much faster. We can also optimize screen space shadow settings, like the number of rays, number of steps, and others. So after tweaking them a bit, the stage does not take much more time than in the case when the shadows are turned off at all. The deferred rendering stage of light environment probes depends on resolution and supersampling of the baked cube map of the environment probe. You can also disable ambient lighting for the probe. The next stage, rendered deferred light voxel probes, performs rendering of voxel global illumination. The most efficient way to optimize it is to disable cubic filtering for ambient and reflective textures. You can also disable reflections at all. Voxel light map resolution and quality have very little influence on rendering of voxel lighting, so that's how we can optimize this stage. Watch the dedicated tutorial to learn the basics of using environment and voxel probes. Render transparent blur surfaces draws all the surfaces having materials with the transparent blur state enabled. This is just a deferred stage, which will be deployed later on the rendering of the transparent blur effect. The less surfaces have this state enabled, the faster the stage will be. The following stage might also be very heavy as it renders screen space reflections. All relevant settings can be found in the SSR section. SSR is a very useful feature providing better look at an acceptable performance cost. Here you can tweak increased accuracy, denoise, resolution, depth, and color of the SSR screen buffer, number of rays and steps used in ray tracing, and roughness quality of diffuse reflections on rough surfaces. Well, our optimizations made this step much faster. The next step is SSAO if ray tracing option is disabled for it. Optimization here involves decreasing buffer quality and resolution. The cavity feature does a little impact and won't give a noticeable performance gain. The next effect is the SSGI. Its settings are on the next tab. It is also rendered separately from the SSRTGI if the ray tracing is disabled. This effect depends on several parameters, such as quality, resolution, and resolution color. Be careful, however, while reducing resolution since it may cause noticeable visual artifacts, while the SSGI stage takes a lot less time. Here goes rendering of additional environment effects, such as background, haze, light scattering, and celestial bodies. We can get rid of this stage by disabling environment in the rendering features list. Environment can be easily replaced with a sky object having a background cube map applied. A vast part of the render environment step will be skipped. One of the last and most important stages of the deferred rendering pass is the composite deferred, which composes the first part of the final image using screen buffers prepared by the previous steps. It may be refined with a user material here, but by default, it depends on active buffers only. You can disable some of them in rendering, buffers list. Anyway, this step is not heavy. The emission surfaces stage is performed only for surfaces with the emission state enabled. The only way to get rid of it is to disable all emissive surfaces or turn off the emission effect. The next stage is pretty similar to the render transparent blur surfaces. Refractive surfaces rendered here will be used later during the refraction effect rendering. To skip this and the refraction stages at all, disable the refraction effect in the rendering transparent features. Here starts the forward rendering pass. The stage is called Render Scene Transparent. It begins with rendering of the refraction effect using the results of the Render Refraction Surfaces step, but the major part is taken by the rendering of alpha blended surfaces. Enable the transparent helper to check if there are any. The lighting of alpha blended geometry is a very consuming operation. We can limit the number of lights affecting transparent surfaces. To do this, go to the Lights section of the rendering settings and reduce the corresponding parameters. Now, all transparent geometry is affected only by one voxel and 2 environment probes. To gain some more performance, disable the Multiple Environment Probe option for transparent objects. Volumetric objects, just like this Sunshafts provider, can be optimized via material parameters. For example, there is no need to use a large number of samples. A lower value gives a similar visual result at lower performance cost. The Render Scene Transparent stage includes rendering of water in worlds with a global water object. Let's take a look at water settings. It is not necessary to use ultra quality for SSR and refraction when it comes to optimization. Reducing anisotropy quality may give you a bit more performance if the water in your project doesn't require rendering of shoreline wetness, underwater shafts, environment, and voxel probes. Switch off the corresponding flags. Field height resolution should be taken into account only if the water interacts with any field heights. A set of more important water geometry parameters can be optimized in the water global base material. These are tessellation distance, tessellation exponent, and maximum tessellation factor, defining the complexity of water surface. Optimizing them can significantly decrease rendering time. The next stage is rendering of volumetric clouds. Their look depends a lot on sampling quality, lighting quality, and samples count. In case of interaction with a field weather object, consider decreasing dynamic coverage resolution. For better performance optimization, consider using interleaved rendering, which performs skipping over every 2 to 4 pixels, and downsampling rendering. Additionally, decreasing the number of samples. But be careful with these parameters since the look of your clouds will degrade a lot. It is possible to speed up the render scene cloud stage up to 100 times at the cost of a realistic look. The next render adaptation color stage is responsible for camera adaptive effects, such as adaptive exposure and adaptive white balance. You can skip this step by disabling the white balance effect and switching to static exposure mode. The TAA stage is for temporal anti-aliasing. Among its settings in the anti-aliasing section, pay attention to the fix clicker, color clamping, fix blur, and anti-aliasing in motion. Velocity clamping is also an important feature, which fixes artifacts caused by pixel offset. It may be performance consuming, so consider switching it off as well. These optimizations gain some performance, which may be necessary for rendering a heavy world. The next stage renders the transparent blur effect. It fully depends on the intensity of the effect, so you can decrease the value to get a bit more milliseconds. The next important stage is render camera effects. It might be very time-consuming, so let's go through its steps. Motion blur is rendered first. It can take much time and cause excessive blurring at higher settings, so keep the velocity parameter low. Limit maximum velocity to prevent enormous blurring of objects moving too fast. Decrease the number of steps to reduce computational load. Disable the camera velocity option if you develop a VR-oriented project, and enable the Neat Silhouettes option to optimize the effect a bit more by disabling additional blurring of geometry edges. Settings of the depth field effect vary a lot and can produce a quite realistic look, but take a lot of time. Always use lower quality since it makes very little difference. Resolution should be reduced carefully as degradation of blurred areas is very noticeable. You can also turn off increased accuracy and focus improvement for better performance. The next post effect is bloom, which adds some glow to bright areas. Let's go to the bloom tab of the camera effects section. Quarter resolution is enough, and the number of passes can be reduced too. We can adjust scale and power parameters to compensate that. The last rendering stage is post-engine materials, intended for post-processing effects. Here, the FXAA effect, an additional anti-aliasing, go first. Switch off the flag to skip the FXAA step. Then go sharpening of the final image to avoid over-blurring caused by anti-aliasing. You can tweak its intensity in the post-process settings section or disable at all via the state in the rendering, camera effects menu. Now we should talk about dynamic reflections. If a surface in your scene uses planar reflections, just like the floor here, let's see what happens in the rendering sequence. A new stage in the middle of the render scene function appears, the render reflections procedure. It is responsible for rendering of planar reflections, which involves rendering of the whole screen one more time. Of course, some screen space effects are skipped, but anyway, it is clear that rendering of a single planar dynamic reflection takes much more time, so you have to be careful with this feature. However, there is a way to optimize it. Open the material parameters of the reflective surface, the floor, and select Lower Map Size for the planar reflection effect. In this case, the reflection will be rendered into a much smaller screen buffer, and the stage will take less time. You can also use screen space reflections instead and adjust bit masking as described in the content optimization video tutorial. Dynamic cube map reflection provided by an environment probe is also a very time-consuming operation. Unlike planar reflection, it renders the screen 6 times, one for each side of the cube map. To optimize it, go to the parameters of the dynamic environment probe and adjust these ones. Faces per frame. Reduce the number of cube map sides rendered each frame. Resolution. It is better to keep it as low as possible. Super sampling. Set it to the default value of 1. Thus, you will extremely reduce rendering time of this effect at the cost of realistic look. So now, the render reflections cube renders the screen only once, which causes a slight lag in reflection. The most preferable way, however, is to disable the dynamic parameter of the probe and bake reflections into a cube map as described in the dedicated tutorial. So, when you don't need dynamic reflections, disable the feature via the rendering menu. There are also some steps beyond the rendering sequence that we should consider. Object grass update cells is one of them. It is intended to update cells of a grass object and is performed in a separate thread. Find such step and press the Tab key to find the most time-consuming instance of it in the whole dump. As you can see, it took about 17 milliseconds, which is too much for grass. In the editor, open grass object's parameters and take a look at the triangle's field corresponding to the number of grass polygons. Such a huge number slows down the update of cells, so we need to reduce it. Step is also an important parameter defining how many cells will fit into the given size. Reduce it to create more cells and take advantage of multi-threaded update. Reduce density to decrease the number of grass blades. Doing this, we decrease the time to almost 4 milliseconds. Another very performance-consuming object is the particle system. Its update function can be found in one of additional CPU threads of the Microprofile. Pay attention to the count field, indicating the number of actual particles at the moment. The number per spawn parameter defines the number of particles created each spawn action. It is better to reduce it. We can compensate it by increasing the spawn rate, which is better for performance. The lifetime of each particle is worth adjusting, since the lower the value, the faster particle will disappear, keeping the total number of particles low. By tweaking only these parameters, we've significantly boosted the update of the particles object. As you can see, there are a lot of things that can be optimized in your scene, and Microprofile is a perfect tool to find them.